Hello. Hi. Nice to see everybody in here. Wow, there's a lot of people in here. That's cool. Hi, my name is Abdullah Joseph. Thank you so much for joining me today. And I would like to talk to you today about this really long title, Privacy Preserving Cryptographic Authentication in Practice. I made a bet with my colleague whether I can say it 10 times in one breath without breaking sweat. I did. I'm happy about it, actually. So I have two goals for today. And one of them is very, very important for me, which is to give you guys an understanding of OPRFs. And in tech, we love our acronyms. You got the RSA, DH, CEH, GPEN, GXPN, blah, blah. There is one more. And the second thing is I want some papanasi by the end of tonight. It's really important for me. For those of you who don't know it, it's this beautiful Romanian cheese donut. Mwah. So that's the two goals I have for today. But let's talk about cryptography right now. So, as I said, I've been working as a software engineer for a while and a security engineer, security researcher, I guess the proper word is, recently. And my clients include ad tech industry, mostly for the last like 8-9 years. I specialize in application security, basically means I love reverse engineering so much. But today, we're going to talk about cryptography, and we're going to talk about a simple, typical registration and login process. And I'm going to show you some issues with it, and hopefully you get to see that there is better solutions in 2023 that we can adapt right now. So here's how a very, very bad website would do authentication. Don't do that, please. So you get a client. It's an iPhone, an Android, whatever it is that you need. And you have a server. And the idea, the super simple, non-technical idea is that the client would talk to the server. Doesn't matter which traffic protocol that you use. They will talk to it, and they will say, hi, my name is Bunny, and my password is Fufu, just like the example in here. The server, in a very bad way, would say, okay, you're a new user. I'm going to register you. I'm going to put this info in the database, and the database would look something like this. To repeat it for 3 times, don't do this. This is very, very bad. But this is a way for a client and a server to communicate together. So, and how to do logins is basically 90% the same process, just a small change. Instead of saving the database, you are actually just querying it. You're seeing, is the input password same as the saved password? Is it the same? Give this guy all the newsfeed and the resources that he needs. If it's not, tell him bye-bye. This is a very bad way to do it. And let's talk about why is it bad. Because in this case, we have the server saving the client password in plain text and the client sending their password in plain text. And as we know in all security conferences, plain text is a curse word. Don't ever say plain text to someone. So the issue with saving things in plain text, which by the way, I have a friend of mine. He owns a pretty semi-famous recipe website. And I told him about this exact topic, and I was telling him, it's like, hey, I made a really cool research. What do you think about it? How do you guys do authentication? And he was like, oh, we actually log the password and don't do any hashing and anything. We just put it in the logs so that in case someone forgets their password, they can call us and we can give them the password. And I told him, it's like, aren't you scared of hackers or data breaches or something? And he was like, we are a respectable company. We will never be hacked like this. So the idea in here is that both of those things are really bad, and these are issues right now. Let's try something better, and this is right now what I'm going to show you is what I would say the standard that I saw in pretty much 95% of websites right now currently operating. You would have the client send the username and password, again in plain text. You have the server saving it, hashed this time. I'm just going to simplify it and say hashed. I'm not going to say with salt and pepper or with a password derivation function or anything like that. You should do that. But for now, let's just keep it simple. And the server would save this thing hashed. And now, when the login occurs, the client again sends the username and password, and they will get it. They will run a hash algorithm over it, and then they will compare it. And they would see if the hashes compare. Now, this is OK, but there is still a problem. The client is sending the password in plain text. The client shouldn't need to do that in 2023. We have cryptography standards that far surpass what we have currently right now. And this is a very, very old way of doing things. And we can do better. Let's talk about why why is this even a problem? Why are we talking about this? It's been working so far. It's been doing a good job. Why is there someone like me talking about this? Well, because of this, guys. 32.8 million Twitter credentials may have been leaked. Harbor Plaza had 1.2 million records, 1.1 billion records from Adhar. There is a website that's, oh, fuck, I skipped through the memes. There is a website called Have I Been Pwned? And the idea is that you guys all know what does the word rainbow table means that, and the fact that there is a tool called Hashcat, which basically reiterates over hashes and can perform calculations on it so that you can do cracking over leaked credentials. The fact that all of those things exist means that there is still a predominant problem that we're not solving. Clients are sending passwords through plain text. They don't need to do that. So now we come to the memes. So usernames and passwords don't need to be sent in plain text. And the server, even if they hash it, even if the hashing is very good, even if you're not using MD5, even if you have salt and pepper, even if you don't log the passwords, you still save hashes in your database. That's not necessary. And today I would love to first introduce you to this topic, and later show you a little project that I did to mitigate this. And thirdly, if you have any questions or discussions, I would love to talk to you about this because I feel like this is a pretty important problem. Now we come to the memes. So, what's the solution? Half-Life 3 and cryptography. I debated with myself whether I should do this thing because Half-Life 3's memes have kind of died out right now, but I'm a millennial. I'm an OG millennial, actually. So I stuck with them. And if you don't know Half-Life 3, please Google it. So let's talk about OPRFs, and this is the topic of today. They stand for oblivious pseudorandom functions. It's a very complicated name for actually a very simple topic. And now I'm going to introduce our ubiquitous and forever living Alice and Bob characters. So the most important thing, this is Alice Cooper, by the way. He's still alive. I attended his concert a year ago. He's fucking good in Belgium. It was really good. This guy is definitely not alive anymore. That's why the black and white is there. So we're going to talk about them because they are the most important characters in cryptography. And the idea of OPRFs is really simple. It's mostly this line. Bob and Alice, they want to compute a number together, but only one of them knows the result. If this sounds like Diffie-Hellman, it sounds like Diffie-Hellman. Don't tell any cryptographer about this because they will chop off your legs. But this is how I see it. It's basically a simple way for two people to compute a number, and both of them will contribute to the creation of that number, but only one of them gets to know the result. I will explain this topic and then explain how is this useful in authentication. So, here's the joke. Don't tell a real cryptographer, ha ha ha. So, we'll talk about OPRF, computation overview, and this is basically how it goes. It goes in 3 steps, and as in every good cryptographic primitive that's been standardized, there is libraries to do this. You don't need to roll it yourself, and I'm going to point you to a few libraries in modern programming languages like Go and Rust that you can use to do this in a very straightforward way. The simplest idea behind OPRFs is that Alice has a secret and Bob has a secret. And for now, we don't need to talk about clients and servers. Let's really think that Alice and Bob are real 2 human beings. Alice has a secret, and it's a number, and Bob has a secret, and it's a number. They exchange. God is coming. They exchange some information in here, and then at one point, Alice will have a function of both his secret and Bob's secret, and that will be the resultant number, which is the OPRF. And the nice thing about it, and here's where the magic happens, the cryptography magic, Bob does not know the result of the computation, but he helped in the computation through his own number. We're going to talk a little bit right now about how to do this. The next couple of slides will be a little bit technical, but I'm going to try to explain it as much as possible. So there is the first step, which is step 0. Both of them need to have a secret. Both of them need to have a number that they need to keep secret that nobody else should know about. And this first part is the blinding. Now, blinding is a concept in cryptography. You can hear about it in a lot of places. For example, blind signatures is a thing. For now, because I want to keep this talk, the owner of a Volvo V40, please report to the station. The owner of a Volvo V40. Anyways, so we got a blinding factor in here, and it's a concept in cryptography. The idea behind it, of blinding in a very simple, non-technical way, is that you're applying a function that can be reversed over a number. So for example, in a very bad, simple cryptography explanation, you can add a 10 to a number, and the reverse of that operation will be negating that 10. So for example, my secret number is 5. I add 10 to it, it becomes 15. I reverse it, I unblind it, it becomes 5 back again. That's a very simple explanation of what is blinding in cryptography. And this is what the first step of what Alice does. They have a number, which is Alice's secret, and they blind it. Now they have blinded Alice's secret, and they send blinded Alice's secret to Bob. Bob does a function called evaluation. And in this case, we're going to talk about what does evaluation mean in a couple of slides. But the idea behind it is that they apply a function of the blinded secret, the one that they don't really know exactly what it is, over their own secret. You see what's happening here? Bob just created a computation with their secret and a secret that they don't know about, which is very interesting. And the nice thing about blinding is that you can unblind it later. And that's the magic behind it. This function is reversible. The blinding function is reversible. So in this way, Alice just created result between their secret and Bob's secret, but Bob had no idea about what is Alice's secret. If you look back a couple of slides, you will see that they don't actually have custody of Alice's secret. They know blinded Alice's secret. And if the cryptography was good, which we're hoping to, they cannot extract Alice's secret from blinded Alice's secret. And that's the idea behind OPRFs. And that's the idea behind it. Now let's go back. Here's a data tracker from IETF in June 2022. And here's basically the function of blinding standardized in very clear format from IETF for any implementer of cryptographic libraries that would like to take a look at it. It's actually very readable. It's very good. And here's the link for it in case anybody is interested. This is version 10. Right now, I think they have a couple of more versions, but they just modified a couple of edge cases. The implementation still remains the same. So let's visit our registrations and logins. Now we're armed with this beautiful knowledge of modern cryptography about privacy-preserving practices. We can go ahead and apply a little bit extra magic that we just learned over the very bad situation that we've had in try number 2, which is the state of the art that we've had for a long time in web technologies. Client sends the password and the username in plain text. And then the server would hash it and then store the hash in here and compare it. That's the login. Now, what would happen if we actually apply OPRF at this step right here? The password no longer needs to be in plain text. The user never needs to reveal their password, ever. They would apply an OPRF of their password. And the server would save an OPRF of their password, which is not reversible. You can't extract the secret from an OPRF, as we've seen a couple of slides ago. Bob has no idea what is the secret, but they're acting upon it. So that's a really interesting thing. The number one use case for OPRFs, which was, by the way, designed outside of the realm of authentication. It was designed as a really cool mathematical principle. But the number one use case for it is authentication. There's a couple of more use cases for it that you can do. We'll talk about them at the end. So now we've discovered this really wonderful way to do it. What's the next step? Let's talk about the opaque protocol, which is a protocol made for authentication. This is for authentication. This is not a cryptographic primitive anymore. If you're thinking about it, this is comparable to OAuth 2 in a similar way. So the idea behind opaque protocol is that it's a protocol, it's a way, it's a description of how to do registrations, how to do logins based on OPRFs as the base primitive for this cryptographic concept. And this is standardized. Cloudflare has been working a lot about it. If you don't know, Cloudflare is a wonderful cryptography startup. I think they're a lot bigger than a startup right now. They've been working actively on it, and this draft is set to expire in January 2023. They already have 2 forward drafts that they've worked on it. This is active, and it's very, very much popular right now. So that's my goal for today. I want to introduce you to this thing. And we're going to talk about the opaque protocol. The opaque protocol, the idea behind it is, as I just said, the client never needs to send their passwords, ever, as a plain text. They would send an OPRF of it. The opaque protocol is actually not the first protocol that talked about this. there's other protocols that worked with something similar. You got SPAKE2, you got JPake, you got EKE. As I said, in tech, we love our acronyms. Which, oh God, we love acronyms. I actually heard Rust is an acronym for something. I really hope that's just a myth. I really hope so. So the idea in here is that if you go into this link, you're going to find some really extremely smart people called the Crypto Forum Research Group, who are like fucking IQ of 400 plus, that basically tell us what cryptography to use today. They found out that opaque is one of the best candidates for using for modern authentication compared to all the rest of these guys. They actually have benchmarks that they ran about it. You can go into the GitHub page and you can check it out. It's really interesting stuff. So, coming back to OPRF and coming back to Mr. Alice and Mr. Bob, right now they evolved. It's like, remember Pokemon or Digimon? It's like revolution right now. So Alice is no longer a human. He's a client. And Bob is no longer a human. He's a server. He's a machine. So the idea in here, Alice and Bob, client and a server, will need to apply the opaque protocol. The opaque protocol is actually a lot simpler than you'd expect. The idea behind it is that Alice is a client. It's a user. It's just like me or you when we're logging into a website, for example, through our Android or iPhone mobile devices. We would have a password in here. Alice secret would be our password. My username, for example, could be my email, and the Alice secret would be my password. Bob would also have a password. The server would have a password. If you know public key encryption, think about it as a private key. That's the private key of the server. Obviously, you'd have to rotate it if you're doing infrastructure work. But for now, you can think about it as a private key for the server. And the idea in here is that the first step you would do is apply an OPRF with Alice's password. If you remember a little bit about how OPRFs work, Alice, in between step 0 and step 1, it's not just one API call. There's a couple. It's a bit of a Sigma protocol. So you do need, as an implementer of this, that's an important thing for you to understand. It's not a one-way non-interactive proof. You do need a couple of things. And then afterwards, step 2 is quite simple. The Alice would actually generate a public key pair. So they would, a key pair, a public and a private key. So one is called Alice private, one is called Alice public. And Bob would do the same thing in here. They would generate an ephemeral key pair. And the last step, which is the most important one, is that you would just encrypt the contents of Alice's private key, Alice's public key, and Bob's public key all together using AES encryption, very standard, with the key being the OPRF. Notice, the key in here is the OPRF. The key in here is a product of a computation that occurred between Alice and Bob that Bob has no idea about, is oblivious about. That's the coming in, oblivious pseudo-random functions. And Bob would go ahead and save this thing in an envelope. That's the nice thing about it. It's basically in a simplified way. If you want to summarize this entire slide in 2 sentences, it's using a discrete proof of Alice's secret as a password, and it's doing a symmetric encryption over it. That's it. The only way to unlock it is through the login, and the only way to unlock it is that Alice would have to create a proper, similar, not the same, similar OPRF, and they would have to use the key over it to do it. And that's very interesting. And after all of this happening, after the login happens, the nice thing about it is that they can generate a Diffie-Hellman session token. Really, session tokens are amazing. We love them in authentication because they are ephemeral. They are computed for both parties. And you don't share them over the wire. And the nice thing about it is that it's ephemeral. It's short-lived. You can cancel it if you want to. Bob can cancel it if he wants to. That's really cool for modern authentication systems. This fits very nicely with the OAuth 2 principles. You can go and have a resource token. You can go and have a token that is used by everybody. And you can cancel it if you want to. You can rotate it, or you can make it long-lived if you want. That's the nice thing about it. It fits very nicely. So the nice thing in here is that, coming back to our slide, Opaque has just solved the 2 problems: the server, client password, and saving the password in plain text. Am I going over time? I think I'm good. All right. So that's the nice thing about Opaque. We solved all the problems. It's wonderful. Oh my God, everybody loves it. Look at this, man. Everybody in here loves it. It's so cool. So Opaque is so nice and cool. Why am I talking about it? This is my daughter, by the way. I'm a new father, so I'm really happy about this. So. Thank you so much. So opaque is cool. Opaque is really nice. And why are we talking about it? This very handsome person is called Professor Matthew Green. He has a cryptographicengineering.com blog, which I highly recommend everybody looks at. It's very, very nice blog about software engineering and cryptography and privacy preserving. Think about him like Bruce Schneier. And he's a very, very prolific person. And the nice thing about it is that he wrote about PAKES back in 2018, a long time ago right now. And there's an internet draft proposal about opaque. But back when I was in 2018, 5 years ago, I read this thing and I remembered this sentence, that there is no production quality implementation of the code. So I said, let me make an SDK about it. So opaque in the wild, we figured out that there is no production grade SDK. People love SDKs. I work in the advertisement tech industry. We love our SDKs. There's an SDK. If anybody in here is a publisher for a mobile game and they're in an ad industry, oh my God, everybody loves monetization SDKs. Everybody loves attribution SDKs. SDKs are all over the world. Actually, I read a statistic which I really hope is wrong from Google, that 65% of an Android app is not written by the user, by the developer. It's written by other people who integrate their SDKs in it. I think that I read that back in 2015. Right now, I think the statistic is like 75%. The scary thing about it, and the nice thing about it, is that we depend on other people's code. So when somebody writes a library, everybody uses it because it's good. So I wrote an SDK about it. It's called Pliskin because, again, as I said, I'm a millennial, escaped from New York. Hello, this is very nice. And I designed this logo myself, so I'm actually quite happy about that. I think this is the proudest art I've ever done, so I'm quite happy about it. So the idea behind Pliskin is that it's an open source SDK that is for JavaScript, for the front end, for the mobile, and for the back end. And it also has a database component to it, database wrappers. It's supposed to be plug and play, using standard cryptography libraries. I say standard because Cloudflare is an innovator, in my opinion, of cryptographic library implementations and application. And the library that I used for all the mathematical calculations, it's called Cloudflare Circle, with no E at the end. And it is a modern cryptography library written in Go, maintained, and it's a very powerful library, and I based Pliskin on it. And as I said, it's written in to be used for the front end, for the back end, and for mobile applications. I've tested them both on Android and iOS right now. JavaScript is running already, and there is types for it for TypeScript, and there is also it's written in Go, so you can compile it for WASM, JavaScript, or shared libraries to be used in the back end. And the nice thing about it is that because it's written in Go, you can use a compiler called TinyGo, maintained by Google, to put it in your IoT devices. So here's how the JavaScript code looks like. I'll spare you with the Android code right now. But the JavaScript code would look something like this. You'd basically just call in here an async await, run password registration. You use an app token, and you'd communicate with your data with authentication server. And then you would get a session token that you can use to talk to the resource server. As you can see in here, I'm using a bit of all-auth 2 terminology. I was going to say criminology. Sorry, terminology. So, and the login is very similar in here. So you would use pliskin.runPasswordAuth, and you can run it with the same username and password. The nice thing about it, and I had a demo about this that for some reason the demo gods refused to let me present it today because the website just didn't work. But the demo was that the database was public. It was on GitHub. The database for this was public. There is no database breaches because what is being saved in the authentication server is, as we said, an OPRF. It's a proof of the password. It's not a hash, and it's not the password itself. It's not reversible. And the nice thing about OPRFs is that if you generate 10 different OPRFs for the same password, you would get 10 different strings, 10 different binary blobs. They're not the same. If you generate 10 hashes over the same string, you would get the same 10 hashes. So as you can see in here, the attacker will not be able to infer any information from an OPRF. That's why the database doesn't even need to be that secure. So that's the idea of using session tokens in here. And the idea of backend deployment is actually quite easy as well. This code would live in the resource server. I will explain a little bit in a small diagram what is a resource server, what's an auth server in a small diagram right now. But the idea in here is that the server itself would use S2S calls, ideally not HTTP. Ideally, you'd use something like WebSockets because this thing will be long-lived, or run both servers at the same place so you don't have to even access or do any networking. And you do it like this, and then you would check if the session token that the user has sent you is actually the same one that is being saved by the resource server. Let me right now explain what is a resource server and a not server. I call it in here business server, but it's in all terms it's called a resource server. And the idea is that Alice wants to log into their favorite website. Alice does a registration, runs the registration protocol. This is where all the OPRF, opaque magic occurs and all of the nice shenanigans occur. And then the auth server in here, running Pliskin as an SDK on their backend, will store the password proofs. And as I said, the auth server can actually remain public. I really don't care if it gets breached because you get nothing out of it. It's just a waste of hackers' time. And then when the login occurs, Alice would communicate and will have a short-lived session token that they would talk to the client about. And then when the resource fetching occurs, when you actually want to fetch your newsfeed or fetch your latest recipe or the latest trend in TikTok. I know actually a guy in here, he's working with TikTok, and oh my God, I'm not a fan. But the idea is that the NPC trend on TikTok is actually quite fun, though. I did like that one. So in here, they fetch some resources with the session token. You can communicate, the client can communicate directly with the resource server, and the resource server would once only check if the auth server is correct, and they would save it as a temporary cache, and then they can keep using it for a day or 2 days or however long the session token should be lived. That is a business decision. And that's basically the idea behind the architecture. The next steps would be for me to get an actual security audit. I was lucky enough to talk to a cryptographer here at this conference, and they were very interested in this thing, so that would be nice. And ideally, it doesn't break my wallet. And make it more platforms, easier usage. Basically have a proper iOS SDK that is not just written on weekends, that would actually be like unit tested, production ready, and all of that stuff. And for you guys to tell me your opinion about the project. So go ahead, fork it, link it, give me some security audits, trash it, make all the issues that saying that stuff doesn't work, and don't give me an explanation why this stuff doesn't work. So thank you so much, and I am done. I wish that, welcome all your questions. Thank you so much.
That was not just super insightful and fun, but also incredibly on time. Okay, let's take questions. We have Joey here. We have some in the back. Let's start.
Hey, Joey.
Hi. You mentioned it's okay if the auth server gets breached because the...
Can you raise your volume a little bit? I'm sorry.
No, but I can talk louder. You mentioned that it's okay if the auth server gets breached or if the database is public. Bob's secret here still needs to remain secret, right? Otherwise, you can perform an offline attack against the protocol?
Bob's private key needs to remain secret. Yes, that is correct. That is very important.
Got it.
Good point.
One further question. Can you comment on the difference between opaque and passkeys?
So I know opaque is the only one that from the Pake family, the family of the maybe I can go a couple of slides before. Yeah, okay, so there is a family of password authenticated key exchange, Pake families that actually have privacy preserving authentications. SPAKE2, JPEG, and eKey. From what I understand, and don't quote me on this thing, but the idea is that I think opaque is the only one that's actually using OPRFs. The rest are not. And I think this is the reason why Matthew Green wrote his post, if I'm not mistaken, right here. If I'm not mistaken, I have to double check that, but I think OPRFs are only used with opaque. That's the idea behind it.
Cool.
I guess there was a couple more questions.
Yes,
I think
definitely.
I can hear you from here.
Could you please, stand up. Thank you.
Hello, thanks for the presentation. It was very good. So I had a question. We love authentication because I can log in from my computer, from my phone at the same time. How do you do this with the secret? How do you exchange it to your phone, or how do you register another device for you to log in?
Okay. So to repeat the question, how do you do registrations from your phone or something like that? And the idea, correct me if I'm wrong, and the idea behind it is that coming back to the opaque protocols registration page, in here you'd have your password, and that password would be saved in your brain ideally, or in a password manager, and then you'd communicate. Let's talk HTTP and networking levels. There, between step 0 and step 1, there will be 2 API calls, one for blinding, one for evaluation, and one for finalization of the OPRF. And then afterwards, so that's 2 API calls, and during those 2 API calls, the resultant of that, it would basically be just the OPRF. There's nothing else. And then afterwards, you'd do the key generation, and you'd send the encrypted information. And Bob would save in the database your name as the key, and the second thing that will be saved is the envelope, right here. So that's basically the idea behind it. And every time that you want to do a login, basically a login in this scenario is a challenge. Bob will send you a blob saying that, hey, you are Alice, I'll send you the encrypted blob. Can you decrypt it? There is a small attack in here, maybe some of you caught. If you make a username enumeration, you can technically get all the encrypted blobs of all the users on that website. But since they are encrypted, and ideally with a strong symmetric encryption, you will get nothing out of it. But that's the idea of a login. The login is basically saying, hey, I will send you this encrypted sealed box. It's your job to decrypt it. And after you decrypt it, we can do the Defi-Hellman session token exchange. I hope that answered the question. We can see each other after the talk if you want to. We can talk about it. So.
That's awesome. Let's go to the next one. Okay.
Yeah, thanks for the presentation. So my question is...
Can you speak louder? I'm so sorry.
Yeah, sure. My question is Alice's secret derived from like a handwritten password from the...
Yes, it is. I skipped this technical detail, but if you look at Pliskin's docs, it's actually derived from a KDF, K-derivation function.
Yeah, I'm thinking that maybe if Alice's password doesn't have enough entropy, then you might not get the full power of oblivious PRFs.
Yes.
So in the event that the server gets breached and the password is predictable, maybe you have some security issues.
That is correct. That's correct. To repeat, the idea is that if there is a technical detail that I didn't include here. It's in the library, but I didn't include it. The idea is that Alice secret is not just like bunny foo foo 333. It should actually be based on a key derivation function with the input being bunny foo foo 333. And the output of the key derivation function is the one that's being used. And the idea in here is that key derivation functions, there is a vulnerability. If you don't use enough entropy, there is going to be a problem. Enough entropy and randomness is a problem that I think will be a little bit outside of this talk. But deriving enough entropy from modern systems, in my opinion, shouldn't be that hard. It's not that hard. It's pretty standard at this point. So if you have a library, an SDK that can do that in a pretty good way with a good enough key space, you should be okay with it. But one of the reasons I created Pliskin, the library, is because doing all of this is really annoying as a developer. I worked as a backend and front-end developer. If somebody gave me this thing and I have to do it in one sprint, I will kill myself. So having a library out of it makes things better. And people can contribute to that library, and one fix will fix everybody's problems. So one more question I got right there. Do we have time?
Over here.
Have you done any benchmarking on the log?
You're going to have to repeat it. There was some construction noise.
Sorry. Have you done any benchmarking on the login overhead? Because hashing is fast, but sometimes you really care about performance. And have you done any benchmarking there?
The question is, what is the benchmarks between with this situation? Hashing is very fast. It's very good. I did some benchmarks just based on a small script. I don't have it public, but the idea behind it is no, this stuff is really not that complicated. The idea behind it, why is it not that complicated? Because you think about what the backend is doing, and the backend in this case is like the person, the machine running Pliskin. Machine running Pliskin it has to do a Diffie-Hellman, and it has to do an AES encryption, and a evaluation function, which the evaluation function is basically just computing some stuff on an elliptic curve. All of those three things are very streamlined in 2023. Hardwares love that. They want to do it. So in my opinion, it's not that hard, but it would actually be a good idea for me to do some benchmarks and put it on the README. So good point.
Yep. Thank you very much.
Thank you for your question.
Thank you so much. This was awesome.
See me outside. Bye-bye.